So, hello, back in the lab here. I wanted to record a follow-up session for CS115 because I realized that in the combined CS115 and 116 session, I spent a bit more time on CS116, particularly with showing how the waveform looks a bit different injected into a real cable after you perform the pre-calibration. I did not do that with CS115. So I want to do that now and show you how significantly different the waveform can look after pre-calibration. So to review, we'll repeat the pre-calibration step just to get anchored, right? Know what the signal characteristics are that we're injecting. This all underscores the importance of the pre-calibration step. You want to inject into a controlled setup, a controlled impedance, so you know what it is you're injecting, because it is going to change once you inject into a real cable under test. So we have our CS115 pulse generator, the Solar 9355-1. We're injecting into our injection probe here in the calibration fixture. 50 ohm dummy load on one side, and we have our 40 dB of attenuation here. I'll come back to that here in just a moment. And our cable going into the oscilloscope, into the 50 ohm input of our oscilloscope. So the amplitude of the drive signal is defined as a current of 5 amps. So that's 5 amps going into our input of our scope, into our 50 ohm input of the scope that we're going to measure as a voltage. So 5 amps into 50 ohms is 250 volts. We don't want to inject that directly. That's how you burn up scope inputs, and that's not a good idea. So we're attenuating that signal by 40 dB, so a factor of 100 for the voltage. So that 250 volts is going to look like 2.5 volts at the scope input. That's a much more manageable level that we can measure on the scope. Okay, so this is all stuff that we talked about in the previous session. So it's just reviewing and kind of getting our anchor points back. So I'm now going to turn on the signal generator. It's already on, it's just the output is disabled. So we're going to turn this on and we're going to have about 30 pulses per second for the spec. I'm going to bring the camera over here so you can see the scope. You can see the signal characteristics. And I'm injecting the full 5 amps per the requirement. We sometimes tailor the limit down to 1 amp, but I'm injecting the full 5 amps. If you recall from the previous session, I said that while looking at the signal characteristics here, you're getting this indication of an impedance mismatch. And so there's some reflections and things, you know, it's just an imperfect waveform. And I'm just going to do a single trip here and disable the signal generator because that clicking is annoying. But you're getting some indications of an impedance mismatch here, which is not too surprising because even if the output of the signal generator is a perfect 50 ohms, I don't think it is, but it may not, you know, it may be, it may not be. But that 50 ohms is going into really 100 ohms here. You got 50 ohms on one side, and then the 50 ohms going into the scope on the other. So you're going to get different amounts of those imperfections with different injection probes. And you can counter that by putting a pad between the signal generator and the injection probe. And this is what I was using in the previous session, a 6 dB pad, right here in line with the signal generator and the injection probe. That'll minimize the impedance mismatch and clean up these imperfections a little bit. But it'll also limit you won't be able to get the full 5 ampere amplitude. So for this part of the demonstration, I want to do the full 5 amp amplitude, and we're going to live with those imperfections. So we'll just take a look at the important characteristics of our signal. I'm going to turn the signal generator back on and do pre-triggering again. So there we go. Now we're continuously triggering on the signal, and we're at 1 volt per division. Let me zoom in on the time base a little bit here. So, okay. And then I'm just gonna do a single capture, disable the signal generator. So the amplitude, the first thing we want is the amplitude of 5 amps. And as we said, that's 5 amps into 50 ohms, 250 volts, divided by 100 through the 40 dB of attenuation. So 2.5 volts. So 1 volt per division. We're sitting here right around 2.5 volts. You're getting a little bit of sag on the top part of the waveform. So I've adjusted it so that I'm at least getting a full 2.5 volts on this falling edge. So we're getting a little more than the 2.5 volts, so a little more than 5 amps on the first part of the waveform. That's okay. I'm going to err on the side of a slight overtest to make sure that we're still getting the 5 amps on this part of the waveform. So the next thing to look at is the pulse width. And we're at 10 nanoseconds per division. So we're at just over 3 divisions. So the spec is minimum pulse width of 30 nanoseconds. And so we have that. Okay, we can't adjust that. We can adjust the amplitude. We can't adjust the pulse width. It's what we get out of this pulse generator, but it's within spec or it's above spec, greater than or equal to 30 nanoseconds. So we're good there. And then last thing really are the rise and fall times. So if we go back to free triggering, and then we'll zoom in on that rise time. And now we are at 1 nanosecond per division. Just adjust the trigger level a little bit here. And we'll get single capture. Okay, so we're at 1 nanosecond per division. And so we are clearly less than the 2 nanosecond spec. Okay, if you just look at the spec in the mil standard and what I showed in the previous session, the spec is less than 2 nanosecond rise and fall time. So we're sitting at about 1.5 nanoseconds. We're good. The rise time is within spec. And then we'll look at the fall time. And we will trigger on the fall time, on the falling edge. And I want to move my trigger up a little bit so we had a little more fidelity on that. Yeah, move that up here, get another trigger. There we go. All right. So same deal. You expect the rise and the fall times to be similar, and they are. So we're just under 2 nanoseconds. All is good. Rise fall times, pulse width, amplitude are all right where we want them to be. So let's get back to being able to see the entire pulse. Rising edge trigger. Okay, so you can see the full 30 nanosecond wide pulse, and you see some of this imperfection down here that's just a function of how the signal generator is interacting with the injection setup. And so this gives you an idea of what the signal looks like into the controlled 100 ohm calibration fixture. Yeah, we'll take one more look at the calibration fixture, and then we'll see how things look into a real cable and give you a closer view here. So here's the injection fixture, 50 ohm dummy load, 40 dB of attenuation going off of the scope. And then the signal generator is hooked up just directly through this cable, no pad, through the input connector on the back of the injection probe. Okay. So now, before we do anything else, we're going to disable the signal generator. I'm going to disable you. You can actually just you can disable the output without turning the unit fully off just by hitting one of these band switches here, and so now the output's disabled. But for extra safety, I'm going to turn the unit fully off. Okay. You don't want it because that's 500 volts you're injecting. You don't really want to be messing around with it while you have an active signal going through it. So generally speaking, this is a bulk cable injection type of test. So you're going to be injecting into a cable, and if it's power cable, it may not be shielded, but for signal cables, in the general case, they're going to be shielded with the shields terminated on both ends. So at low frequencies, it's going to, at DC, it's going to be a short. So, EMI and RF, we know that there's really no such thing as a dead short, not at all frequencies. As you go up in frequency, the loop inductance is going to have an effect, the capacitance is going to have an effect. So the impedance is not going to be zero from DC to daylight, but at low frequencies, it will look like a short. So we can represent that type of configuration with a short. I'm just going to do it with a piece of wire. I'm going to start with a short piece of wire. We'll go to a longer piece of wire to further illustrate the point here. But I'm just going to put a loop of wire through this and short the ends together, so we have our short, and it will be our cable under test. So remember what that waveform looked like, and now we're going to see what it looks like when we inject into our real test article or test cable. So I'm going to get the what it's worth. Let you see what I'm doing here when I get the probe out of the test fixture. I prefer these other probes that actually have a clasp or a clamp that you just pop it and then it opens up. This one has a screw or a bolt, so it takes a few seconds, but not a big problem in the grand scheme of things. One other thing to note before we hook this thing up, like this, we're going to be monitoring the current directly with a current probe, but all current probes are not created equal. So let's talk about that for a second. We're looking to measure something on the order of 5 amps, actually a bit higher than that. I'll get to that in just a moment. But we're measuring in the time domain, and we're looking to measure the rise and fall times of a little bit under 2 nanoseconds. So the ideal thing would be to use an actual scope current probe, but we don't have one that goes up to a gigahertz. And they may be made, but they're probably pretty expensive, but we don't have one for this scope. So I do have a probe that goes up to a gigahertz. It's this Fisher F65. If you can read the model number here. And there's that arrow on there that we marked that's just with a Sharpie. It doesn't come that way, but we marked that with a Sharpie to indicate the direction of positive current flow. So that's handy for doing time domain measurements. Frequency domain, you generally don't care. You just want magnitude. But if you're looking in the time domain, it's handy to know what direction is positive current flow. So I'm going to hook that up in this, in the direction going toward the scope, or coming out of this direction of the probe, consistent with how we did the calibration. But this F65 current probe works up to a gigahertz, and it has a flat transfer impedance of 1 ohm from about, I believe it's a couple megahertz up to a gigahertz. So it's good for using. We can use this for time domain measurements at higher frequencies in the range of this waveform here. We're looking for those rise and fall times of about 1 to 2 nanoseconds. So we should be able to see that with reasonable fidelity with this. It's the best current probe that I have for being able to look at that. And the 1 ohm transfer impedance means that what we see in volts on the scope equals the current in amps. So if we're looking to see, if our starting point is that we're looking to see something that's about 5 amps, then we're going to see about 5 volts on the scope. Okay, so that's our starting point, but more nuances to consider. Again, we're dealing with what is not necessarily an impedance match system. You've got a 50 ohm source impedance nominally, approximately 50 ohm source impedance coming out of the signal generator, and then we're going to be injecting into at least what is effectively a dead short. At low frequencies. So we know it's not going to be an impedance match. So if we first look at it that we're really going to be injecting into a dead short, well, the signal we pre-calibrated had our 50 ohm source impedance, and if we assume that was perfect, going into the pair of 50 ohm resistors in the fixture. So you have just your signal source, your perfect signal source upstream of the 50 ohm source impedance. So then you have the 50 ohm source impedance going into a 100 ohm load, effectively, or pair of 50 ohms in series. Well, you would expect the maximum current, or the current into a dead short, could be about 3 times higher than what we saw in the cow fixture, right? We were tapping off of one of the 50 ohm load resistances, right? So we were only looking at half of the injected potential in the fixture. The other half was being dropped across the dummy load. So the current that we may see into our dead short could be 3 times higher than our calibration level. One other little nuance, this is all stuff I thought about as I was doing some pre-measurements before recording this for your benefit. Because we're injecting, we have an impedance mismatch. We have a 50 ohm source impedance injecting into a dead short, which is really going to be, the complex impedance that we are presenting with our load, the inductance and capacitance. We could get some overshoot. In fact, we will. I mean, as we'll see. So if our pre-calibrated current is 5 amps into the test fixture, and then from the previous discussion, we say it could be as high as 15 amps. Okay, because now we're dropping all that drive potential across the single 50 ohm resistor instead of 3 in series. But now with possible reflections, we could as much as double that level. Okay, so that 15 amps now could be as high as 30 amps because we're going into a mismatched load. Okay, so we can expect the level to be as high as 30 amps. So we need to allow for that. So 30 amps into this current probe is going to produce 30 volts at the output. And I'm limited to a range of plus and minus 5 volts on the scope, or a total span of 10 volts. I'm going to keep the 0 line in the center. So I'm limited to a span of plus minus 5 volts. And if I could see as much as 30, okay, that's a bit high. So I'm going to want to put some attenuation at the output of my current probe. So 20 dB should do it. I'm just taking one of these 20 dB attenuators. So it's the 40 dB is made up of 2 20 dB attenuators in series. So I'm just going to take one of these, one 20 dB attenuator. That's going to knock the signal down by a factor of 10. So if my expected range could be as high as 30 amps, giving me 30 volts at the output connector of the current probe, then the 20 dB attenuator could knock that down to a maximum level of about 3 volts at the output. So I'm going to be looking for a maximum level on the order of 3 volts on the scope. So now we have our injection probe. We have our monitor probe. Now we just need our cable under test. Normally you would clamp them around the cable under test, but because it's just going to be this loop of wire that I'm just going to connect together, I can just run that through both probes. Okay. So I'm just going to do that. And so I have this short loop of wire. It's going to have some inductance, some capacitance. I don't really know exactly what those are. I could ballpark them, but that's a subject for another discussion. So just generally good practice to not have metal touching the ground plane here. You can help it. So I'm just insulating things from the ground plane a little bit here. So we're injecting onto our loop of wire, and then we're going to monitor the current. And I've left the signal generator alone. The pre-calibrated level should be. Sorry, I'm looking at the wrong one. There we go. I've left the signal generator settings alone. So when we turn it on, it should come up to the same level where it was what we pre-calibrated it to. So one more look over here at what we're looking at what we're injecting, and then we'll turn on. We'll look at the scope. So signal generator connected to the injection probe, and we're injecting that EMF in the loop form between our cable and ground plane, and then we're monitoring the cable, the current that we're the resulting current on our cable under test, which is just our wire loop. Okay, and the arrow that I mentioned, that I pointed out, the arrow is pointing in this direction, which is consistent with the direction going into the scope, the way that injection probe is oriented in the test fixture. So we would expect the positive direction of the pulse to still be going upward on the scope. So with that, we go back over here to the scope. Okay, and then we will turn the signal generator on. And we are still set for 1 volt per division. So here's the 3 volt line. So that's kind of where we would expect the maximum to end up. And there we go. Adjust the trigger level a little bit here. And interesting looking waveform. Okay. We are exciting the natural resonance of the cable configuration. But let's zoom in and look at a couple other things here. I'm gonna let it free run here. All right, I'm gonna go to 10 nanoseconds. Excuse me. Oh, sorry, went too far. 10 nanoseconds per division. That's where we are here. Okay, so we'll pause that. That's 10 nanoseconds per division. So there's our 30 nanoseconds here. So the rise time of our drive signal in the test fixture was less than 2 nanoseconds. Well, the cable's clearly not responding that quickly. It's the inductance, capacitance, just the impedance of that configuration is slowing down that rising edge. That's the response to that fast rise time. The rise time is very fast to excite whatever the natural response is of your cable under test. So that's one of the things that I wanted to point out, is that's one of the ways in which the signal going into your cable under test can look very different. Okay. So this is the 30 nanosecond span, or the pulse width. And then here is the falling edge. Here's where you reach the end of the 30 nanosecond span of the plateau part of the drive signal, and here's where it comes down, right? And now you get a bit of overshoot. It's going a bit past 0 because, I mean, you have inductance and capacitance in that cable configuration. You could do a circuit analysis to understand the LC circuit that you're exciting. That's a subject and a project for another day. But I think just from a qualitative standpoint, you can figure that there certainly is some inductance and capacitance. There is clearly some kind of LC response going on here. Turn the signal back on, and now get a single trigger here. Get a nice. There we go. That's about as good as that's going to look. That's clearly a damped sinusoid kind of response. That is the response, the natural response of this cable configuration to that stimulus. Okay, the CS116 is modeling this kind of behavior as a stimulus signal directly, where CS115 is just trying to excite the natural response of your cable configuration to its response to a very fast rise and fall time drive signal. And so our amplitude here, when we look at the peak amplitude, let me zoom in on the time base here. So 1 volt per division. That's almost 2.5 divisions, so it's about 2.5 volts. So call it 2.4 volts. So that's about 24 amps. So that makes sense given the previous discussion that you have the two factors that your 5 amps injected into a total of 150 ohms, your 50 ohm source impedance into a 100 ohm test fixture, that the peak current could be about 3 times higher than that. That's one factor. The second factor is that you're injecting into a mismatched load, so you could have as much as double the signal amplitude. I mean, you're injecting into a short, into a low impedance, so the current, which is what we're looking at, could double, right? The reflection coefficient into a perfect short for the current is 1. It means that the current can double at the load. So it's not quite doubling, but it's close to it. And so when I took these measurements before recording this for you, I remembered that factor. I was expecting that it could go up to 15 volts or 15 amps, but when I saw that it was going up to 24 amps, I remembered the reflection portion of it. So it could go up as high as 30 amps, and it's going up to 24, and that makes sense. If it was going higher than 30 amps, I would have to go back to the drawing board and sharpen my pencil and think about the physics of why that's happening. But this makes sense when you consider those factors, and this is the sort of stuff to think about when you're injecting into a real cable under test, that the waveform is going to look pretty substantially different from how it looked into the test fixture. But the pre-calibration into the test fixture is an extremely important step so that you know what it is you're injecting into a controlled impedance. And then when you go to your cable under test, you inject that pre-calibrated level, and the resulting waveform just is what it is, and you record it. You know, you record the waveform that you injected into the test fixture and put that in your test report, and then you record this level, or you record this waveform at as many different time bases and amplitude scales as you want to get a good fidelity on the signal, and say, okay, this is what we got into the cable under test. But I think this is a good illustration of, well, a couple of things. Just the basic idea that the waveform that you can get into the cable under test can look substantially different from your pre-calibrated waveform, and that's okay, that's expected. But this really clearly illustrates the natural resonance that you're exciting with that stimulus, and that it's a damped sinusoid, which is a very common response. You got the natural resonance that just dampens out over time. For what it's worth, that's 100 nanoseconds per division, so that's about a little more than 100 nanosecond period of that ringing waveform. So if it was exactly 100 nanoseconds, that would be about 10 megahertz. And again, you could do some analysis to determine the approximate inductance and capacitance, and you know, see if that the LC combination gives you something that would explain that. Again, that's a subject for another day. I mostly just wanted to show you that the waveform will look rather different into a real cable under test. One final thing I wanted to show you is just, I'll just put a different length of wire in there. Okay, and I'm going to turn the signal generator fully off. Okay, so I'm going to remove. Handy about using these as our test cable. They come in and out of it very easily. I'm just going to put a longer length of wire in there. Same type of wire with, you know, with banana leads. So this one's about 3 times as long. So let's put this through here. So this should have a bit more inductance, a bit more capacitance. So the total impedance will be a little more. So we might expect that the peak current should come down a bit. So there we are. Go back here. This is just the previously triggered waveform. So let's go back to auto triggering. So you'll know when the new waveform comes up. So we're still just at that pre-calibrated level. So remember, we were getting 25 amps. So 2.5, or it's about 2.4 volts on the scope. So 2.4, well, going back through our 20 dB attenuator, that's 24 volts coming out of the current probe, which corresponds to 24 amps. So that's what we're getting with the shorter length of wire. Now turn our signal on, and that's what we get. So now we're still at 1 volt per division. So that's right around 1.5 divisions. So that's about 1.5 volts on the scope. 15 volts coming out of the current probe, so 15 amps. So that's right around the 15 amps that we would get, not assuming reflections, just going with our circuit analysis of our 50 ohm source impedance going into the 100 ohm fixture, that we would expect the current to be as high as 15 amps. We're still going into a mismatched load. So I think it's just more coincidence that I mean, you can see that we hit the 30 nanoseconds. We'll go ahead and zoom in on this. I'm gonna go ahead and change the vertical scale just so we have a little more fidelity on the signal. So that's now 500 millivolts per division. So that's still a 1.5 volt peak right there. So change the trigger just a little bit, and there we go. Okay, so that's 10 nanoseconds per division. There's our 30 nanosecond span of our stimulus signal. So now we can see that it's slower than what we had with the shorter cable. Just the response, the inductance, the capacitance of the longer cable is slowing down that rising edge a bit. So and we're probably not even at the end of travel here, right? It looks like if the pulse width of our drive signal is wider, that should still keep going up. It's just that we're hitting the falling edge of the drive signal now, and then the signal comes back in the other direction. But this is noticeably slower, and as we would expect for the longer length of wire, and the waveform looks pretty different. Let's get this going again. I mean, it looks similar, but it definitely has a different characteristic. It's a sharper edge here, but I think that's, as I said, I think that's mainly a function. Hang on here. There we go. I think the sharp edge is just that just is where you are on the waveform at the end of that 30 nanosecond period of the plateau of the drive pulse. And then you hit the falling edge, and now you're getting the response to that sharp falling edge. And then you're getting more of an indication of the natural resonance, because after that falling edge of the drive pulse, then it's nominally returning to zero, including some of the noise and reflection stuff we saw on the calibration signal. But you're seeing more of the natural resonance from the falling edge here. And the period here for the period here of our ringing waveform is a little bit hard to see because the damping is more significant. We're only getting like a fraction of one period here, but it's something on the order of that's 40 nanoseconds per division. I'm gonna go to 100 nanoseconds per division just so I can see it more clearly. Let's get another trigger here. Start fresh. Okay, so at 100 nanoseconds per division, that's actually not the best waveform. There we go. Got a little more of a look there. So if our period is about here to here, it's about 150, somewhere between 150, maybe 180 nanoseconds. So it's a little bit longer than it was with the shorter length of wire, at 100 nanoseconds. So the response is a bit different, which you would expect, but it's got the same general characteristic. Right, you're getting the natural response to that falling edge. You're getting maybe one cycle of a damped sinusoid, and then it basically falls below the noise floor. But the specifics are less important than just the general observation that these waveforms are going to look very different from, are likely to look very different from that nice square wave or that nice rectangular pulse that you get in the calibration fixture into the controlled into that controlled impedance. And that's okay, that's expected. So I just wanted to show you these couple of examples of how different that can look. And when you hook into a real cable, you know, in your test configuration, it may look different still. But you can still find some salient characteristics that that can help you make sense out of what you're seeing. I mean, you should see some kind of a rising edge for about 30 nanoseconds. And that's your response to that rising edge. And then you'll see some response to the falling edge. So when you see a waveform like this that looks very little like your drive waveform, your nice calibration waveform, that's okay. Don't get alarmed, and you know, zoom in on the scope, and you know, you can start interpreting what you're seeing. But you're seeing the cable's response to that drive signal, primarily to the fast, you know, 2 nanosecond rise and fall times. That is the entire point. It's giving you those fast rise and fall times to stimulate the cable and give you that response, and then just see how much of that energy is coupling onto internal signal lines that causes some perturbation that you might observe in your equipment under test. And that's really the whole point of the test, is how susceptible is your equipment to these kinds of transients that would maybe impinging on these cables that are connected to your box. So that is basically what I wanted to show you. Change this a little bit here. So that is what I wanted to show you. Just you know, CS115, all of these test methods have their nuances, but CS115 is something of a nuanced test method. If you're not used to it, things can look a little weird. Even the jagged nature of the signal on the waveform that you get out of the cal fixture can be a little disconcerting if you haven't seen it before. You know, and then you see this, it's like, well, what happened to my nice clean waveform? Well, that's okay. You're getting the response of your cable to that stimulus. So that's what I wanted to show you. Thank you for watching, and I hope you found this helpful.